Okay guys, in this video we're going to be talking about the molecular orbital theory approach to electronic structure for molecules. And although it has similar aspects to the valence bond theory, that is, there's atomic overlap involved, there's sigma bonds and pi bonds, it's actually a completely different approach to electronic structure. Okay, so let's talk about what makes molecular orbital theory a different approach to the electronic structure of molecules. Well, first, as the name suggests, we're going to be working with objects called molecular orbitals. Now, molecular orbitals are different. They're not the same as the hybrid orbitals that we talked about in the previous videos. Molecular orbitals are linear combinations of atomic orbitals on different atoms. Contrast that with hybridized orbitals, which are linear combinations of atomic orbitals on the same atom, usually the central atom of the molecule. So that's how molecular orbitals are different from orbitals within the valence bond theory. Another difference is that in molecular orbital theory, the molecular orbitals that we construct are really delocalized over multiple atoms, sometimes over the entire molecule. And that's very different from the valence bond theory, where the electrons are generally confined between two atoms only. So that's another major difference between the two theories. Molecular orbitals are wave functions, and they are built up from atomic orbitals, which are also wave functions. And so when you combine atomic orbitals from different atoms in different ways, it leads to constructive interference in some regions of space and destructive interference in other regions of space. And so we can distinguish between different types of molecular orbitals. Some of the molecular orbitals that we're going to be forming are called bonding orbitals. Bonding orbitals lead to electron density concentrated between atoms. That's why they're called bonding orbitals. Contrast that with anti-bonding orbitals, where we are going to find that there is a node between the two atoms. That is, the wave function, the molecular orbital wave function, will go to zero between the two atoms. That tends to destabilize the molecule. So if you put electrons in an anti-bonding orbital, it causes the energy of the molecule to go up. If you put electrons in a bonding molecular orbital, it causes the energy of the molecule to go down relative to the separated atoms. So we're going to have bonding and anti-bonding orbitals. We are going to have sigma-type orbitals, that is, they're going to have that same cylindrical symmetry, or we're also going to have pi-type orbitals. But now in the molecular orbital picture, we're going to have both bonding and anti-bonding type. And so the star, it denotes an anti-bonding orbital, whereas just a sigma with no star denotes a bonding orbital. And we have the same thing for the pi orbitals. Well, it's helpful to look at pictures, and so let's talk about some sigma-type molecular orbitals. So let's just start with the simplest case of a diatom, and this could be H2, for example, diatomic hydrogen. Right? You have one hydrogen atom. This is its 1s orbital. You have another 1s orbital on a different hydrogen. What we're going to be doing is combining these two waves together. And we can combine them by adding them, or we can combine them by subtracting them. And so when you add the two wave functions together, you wind up getting electron density that can be shared between the two atoms. Okay, and so this leads to a bonding orbital. It has the sigma type of structure in the sense that if you look down the bond axis, you'll see that it has a circular or cylindrical symmetry. And since it's composed from s orbitals, we'll call it a sigma s orbital. If you look at the subtraction of the two atomic orbitals, you end up forming a node between the two atoms. So the wave function, this molecular orbital wave function, actually goes to zero right in between the two atoms. It has a nodal plane. And so this is what you get for the anti-bonding case. And so this would be a sigma star S. The reason it's sigma is because it still has that cylindrical symmetry. If you look down the bond axis, it's cylindrically symmetric. And it's formed from s orbitals, so it's still sigma s, but the star denotes that there's going to be a nodal plane between the two atoms. Okay? And so this destabilizes the molecule. Notice that the energy of the bonding orbital is lower than the energy of the atomic orbital, so it's got this arrow. Energy goes up in this diagram. So the bonding orbital stabilizes the molecule. The anti-bonding orbital, if you were to put electrons in it, would destabilize the molecule. Down below, we have another example of forming a sigma-type molecular orbital. This time we are going to be building the orbitals from p orbitals. So here we have two p orbitals on different atoms. So we have this, these two dots here represent two distinct atoms that are separated in space. And what we're going to be doing is adding this wave to that wave. They are phase matched in the sense that between the two atoms, you're going to have a buildup of amplitude in the molecular orbital wave function. And so this is going to lead to electron density being shared between the two atoms. That's the bonding type of orbital. If you were to change the sign of the phase, that is, if you were to switch the positive phase with the minus phase and then add these together, you're going to have destructive interference occurring between the two atoms. Okay? And so this is going to lead to a node right in between the two where the molecular orbital wave function changes from one sign, or the amplitude of the molecular orbital wave function changes from one sign to another, goes through zero. So here there's a depletion of electron density between the two atoms, and that's destabilizing. So both of these, the bonding and anti-bonding, are sigma type because if you look down the bond axis, it's circularly symmetric. Same thing here. And if these are px orbitals, then we would call them the sigma px and the sigma star px. On this slide, we're looking at the formation of pi-type molecular orbitals. So here we've got two, let's call them pz orbitals. So this is a pz orbital, that's another pz orbital on two different atoms. If you add these two waves together, you're going to get constructive interference above the plane, constructive interference below the plane, and so this is going to lead to electron density being shared between the two atoms. Not directly between them, not along the bond axis, but both above and below this plane. Okay, so this is a bonding orbital. This is a pi bonding orbital. If you were to flip the sign of the amplitude for one of the waves, okay, now this time you've got, let's call this negative amplitude and this is positive amplitude. When you add these two waves together, these are going to give you destructive interference between the two atoms. Okay, and so there's going to be a nodal plane where the wave function goes to zero as you go across the nodal plane. Right? You start with negative amplitude, then it goes to zero, and then you're to positive amplitude. So here there's a depletion of electron density between the two atoms, which is anti-bonding and destabilizes the molecule if you were to put electrons in it. This is called a molecular orbital energy diagram. Okay, and what it does is it depicts the energies of the atomic orbitals relative to the molecular orbitals that we're forming, and it takes into account the electrons in the molecule. So here we're making diatomic H2. Okay, so each side of the diagram represents the orbital energies for the isolated atom. And so hydrogen has just one electron in its, and in its ground state it's occupying a 1s orbital. Okay, so we have two ground state hydrogen atoms. Now the molecular orbitals are represented in the middle here. The bonding orbital, which is constructed from the 1s orbitals and has a sigma type, is lower in energy than the anti-bonding molecular orbital. Now, what we want to do is then fill in the electrons that each atom contributes, fill those into the molecular orbitals. And this will allow us to construct a molecular electronic configuration, right? We worked with electron configurations for atoms previously. Now what we're going to be working with are electron configurations for molecules. And we use, Hund's rules type of approach. Probably Aufbau is not the correct thing to say, but Hund's rule is the correct way to say it. So here we've got 2 electrons in the molecule. And each molecular orbital, just like their atomic orbital counterparts, can hold 2 electrons, one spin up and one spin down. Right? That's consistent with the Pauli exclusion principle. And so since diatomic hydrogen has 2 electrons, they both go down here into the sigma 1s bonding orbital. Okay? And so the molecular electronic configuration for the ground state of H2 is sigma 1s with 2 electrons in it. You could imagine exciting the molecule. For example, you could take one of these electrons and promote it up to the sigma 1s star orbital. And this would give you an excited molecular electronic configuration. Or if you were to consider helium, right? Helium, if we were to modify this diagram, the electronic structure for helium would look like this. You would have 2 electrons in each atom. You would still have the sigma 1s bonding orbital, and up here you would have the sigma 1s star. Now we've got 4 electrons. 1, 2, 3, 4. Each molecular orbital can hold only two electrons. So the molecular electronic configuration of diatomic helium would be sigma 1s2, sigma 1s star, with 2 electrons in that orbital. Right? So I had 4 electrons total. I've got to fill up the molecular orbitals with those 4 electrons. 2 go into the bonding. The other 2 can only go into the antibonding. A couple of terms at the bottom that you want to be familiar with. The term diamagnetic, we may have talked about this in the context of atoms. Diamagnetic means that there are no unpaired electrons. So for example, the ground state of hydrogen is diamagnetic. This helium-2 structure would also be diamagnetic. The term paramagnetic means that we have 1 or more unpaired electrons. And so this excited state of hydrogen would have unpaired electrons. And so we would say that it's a paramagnetic species. Another term that we need to know when talking about molecular electron configurations is the bond order. And this is similar to what we've discussed before, with respect to single, double, and triple bonds. You can actually calculate the bond order using molecular orbital theory. And the definition of the bond order is that it's 1/2 the number of bonding electrons minus the number of antibonding electrons. And so what we'll do here is we'll calculate the bond orders for different diatomic molecules here. So let's just go ahead and look at what we previously had. Here is the molecular electron configuration for hydrogen. The bond order is going to be 1/2 the number of bonding electrons, which is 2, minus the number of antibonding electrons, which for H2 is 0. Okay? So a bond order of 1. So that means the molecular orbital theory predicts that H2 will have a single bond, which is exactly what you get from the Lewis structures. Okay, so there's consistency between molecular orbital theory and what we've learned so far. What if you were to consider the cation of H2, so H2 plus, right? We would need to take away 1 electron, and so we would have a sigma 1s, 1 molecular electron configuration. There, the bond order would be 1/2 times 1 minus 0, a bond order of 1/2. So the bond between the 2 hydrogens in H2 plus is weaker than the bond between the 2 hydrogen atoms in neutral hydrogen. Helium. Diatomic helium. Well, the electron configuration was sigma 1s2, sigma 1s star 2. The bond order, 1/2 number of bonding electrons, 2, minus the number of antibonding electrons, 2, gives us a bond order of 0. Molecular orbital theory is telling us that diatomic helium, helium-2, is not a stable molecule. And in fact, it is not. Experimentally, diatomic helium is rarely encountered. It's a very unstable species, and so it won't last very long, even if you could form it. Certainly, it doesn't form a covalent bond in the sense that we're talking about here. For helium-2+, what if you took a cation of helium? Well, here we would have sigma 1s2, remove one of those electrons, sigma 1s star 1. Now the bond order is different. It's 1/2, 2 minus 1. We have a bond order of 1/2. So that's a weak bond, but the helium-2+ cation is technically stable. Okay, it will have a bond order of 1/2, which means it's weak, but it's still there's still a covalent bond there. And if you were to make the doubly charged cation, sigma 1s2, well, that's going to give you back to a bond order of 1. So there's going to be a full sigma bond between the two helium atoms in the doubly charged cation. Okay, so this is going to be a stable cation. All right, so that's what molecular orbital theory predicts for these hydrogen and helium diatoms. What we're looking at on this slide now are homonuclear diatoms from group 2 of the periodic table. So there's a couple of factors that we need to consider, because now when we start going to group 2 atoms, we have to consider both the overlap of s orbitals and the overlap of p orbitals. And the two factors that we want to consider is that the atomic orbitals, when they interact to make molecular orbitals, they interact strongly when there is little to no energy difference between the two atomic orbitals. So, for example, in a diatom, a 2s orbital on one atom would interact strongly with the 2s orbital on another atom. However, the 1s orbital on one atom will not interact strongly with the 2s orbital on a different atom, because the energies are very different from one another, right? 1s electrons, 1s orbitals have a very low energy compared to 2s orbitals. Same thing with 2s and 2p orbitals. They typically don't mix that much. It varies, but you can think of them as being as not mixing with each other. And so really you only have to worry about s orbitals mixing with, you only have to worry about 2s orbitals mixing with other 2s orbitals and 2p orbitals mixing with other 2p orbitals. Another thing that needs to be in place is that the atomic orbitals that you're talking about, they need to have a strong overlap. And so I think I might have, no, I don't have a very good diagram of that, and so I'm going to show you an example of two atomic orbitals that would not interact very much. So let's look at, here we have two atoms. Consider the 2s orbital on one atom, and then consider a 2p orbital like this on another atom. Now, you might have favorable overlap between this 2s orbital and this portion of the 2p orbital here. However, you're going to have destructive interference between the 2s orbital and the lower lobe of the 2p orbital. So between these two atoms, between these two orbitals, there is not good overlap. They will not strongly couple together to form molecular orbitals. So you don't have to worry about this type of interaction. as well. Anyway, let's go back to this, this diagram here, and let's look at what we see. So what you're looking at here, this is going across the periodic table, starting with diatomic lithium, diatomic beryllium, all the way up to diatomic neon, and it's showing you the relative energies for the molecular orbitals that make up the valence shell of the molecule. And so this lowest energy orbital that they're showing is the sigma 2s orbital. Way down below, probably in the basement, would be the molecular orbitals that are constructed from the 1s atomic orbitals. Here we're just dealing with the valence electrons. Okay, and so you can see the bonding orbital that forms between the 2s orbitals on each atom. And as you go across the periodic table, you see that the energy drops. That's a general truism. All of the molecular orbital energies kind of go down as you go across the periodic table. Some go down more than others, as you can clearly see. Anyway, here's the sigma 2s. And then this orbital, this is the anti-bonding orbital corresponding to that overlap of 2s orbitals, 2s atomic orbitals. Okay, so this is the bonding and anti-bonding for the 2s combination. Here on lithium, these are the pi bonds that form between the p orbitals. I'm going to go ahead and show you two atoms again. So here you've got good overlap when you've got two p orbitals like this. Okay, and then another way to draw it would be a distinct pi orbital overlap would be like this, where the p orbital is coming out of the plane of the page, and so you've got good overlap here and here. Okay. Those are the two types of bonding orbitals that we're looking at here, this one and then that one, the other one. Okay. You see that those don't change that much as you go across the periodic table. The orbital here, this sigma 2px, that one looks like this, where you would have the two atoms, and then you would form, if they add together like this, you're going to have electron density forming between them. So this is the bonding orbital for the 2px atomic orbitals. And you see that those involve a fairly dramatic drop in energy compared to the others as you go across the periodic table. So much so that you have this sort of crossover where before you get to that point, the pi orbitals are lower in energy for nitrogen through lithium, but as you go past into oxygen, fluorine, and neon, you see that the sigma bond is lower in energy than the pi bonds. Up above that, you have the anti-bonding, the corresponding anti-bonding orbitals. So these are the two pi bonding orbitals. If you flip the sign of one of the orbitals, that's going to give you the anti-bonding configurations. Likewise, if you flip the sign of this orbital, it's going to give you the anti-bonding sigma 2px orbital. Okay, so that's what these lines represent. They represent molecular orbitals that are formed between these particular atomic orbitals. Notice that the pi orbitals, there's two of them, and they're degenerate. Okay, so there's two equal energy pi orbitals, and that's significant, that's important. So what we're looking at here, this is a graphical example of constructing, it looks like a diatomic beryllium cation. Okay, so here we're looking at just the valence electronics, the valence orbitals, and beryllium has two valence electrons, and so beryllium 2 plus is going to be short one electron. So let's say that this is a neutral beryllium atom, and then over here this is a cation, beryllium cation with a +1 charge. And so what I've drawn out here, these are the molecular electronic configurations. Here, this part, the sigma 1s and the sigma 1s star, those aren't actually shown in this diagram. They would be downstairs in the basement. Those would involve the core electrons of beryllium, right? Each beryllium atom would have 2 core electrons, and so those don't really contribute to the bonding in the molecule, because you have both the bonding and the anti-bonding are occupied with electrons, and they effectively cancel each other out. And then in this notation here, they're just simply being denoted by a filled K shell on each atom. So recall that the subshells, as I'm sure you remember, they have letter names, right? S orbitals, P orbitals, D orbitals. But the value of the principal quantum number, 1, in the case that we're discussing right now, that also corresponds to different atomic shells. And the lowest energy one is called the K shell. And so that's why we have this KK. It represents the core electrons on each beryllium atom, which are filled with electrons. Then we have the valence electrons. Okay, and so since we've got 3 valence electrons in the beryllium 2 cation, the diatomic beryllium cation, we've got a total of 3. So we've got 2 electrons here, 1 electron there, for a total of 3. 1, 2, 3. So we have 2 electrons occupying the sigma 2s, and 1 electron occupying the sigma 2s star. So this is the molecular electronic configuration. What would be the bond order? You don't have to worry about the core electrons at all. It would be 1/2 times the quantity 2 minus 1. So we're going to get a bond order of 1/2 for this cation. Would it be diamagnetic or paramagnetic? You see that it's got an unpaired electron, and so we would say that it is a paramagnetic molecule. So here's an example where we're being asked to determine whether diatomic oxygen is paramagnetic or diamagnetic, and we're also being asked to calculate the bond order. And so what we're given, and this is what you'll be given on the exam if you need it, we're given the ordering of the molecular orbitals. That is, we're essentially being given the empty diagram for the molecule. And so we're being asked to fill it in. And so it's helpful to start with oxygen, just the atom. So you'll have, the 1s orbital is filled, 2s, 2, and then it's going to be 2p, 4. Right? So this is the atomic electron configuration for oxygen. And so you've got, for the O2, okay, you're going to have the filled 1s orbitals. So each oxygen atom is going to have a filled K shell. And so we just represent that by this K times K. And then what we're going to have is the ordering that's given on the problem. So there's a sigma 2s, a sigma 2s star, sigma 2p, pi 2p, pi 2p star, and sigma 2p star. And so what I'm going to do is I'm going to go back to the diagram and show you that. Okay? So what we have here, this is the sigma 2s at the bottom, the sigma 2s star anti-bonding. Then you have the sigma 2p, here they're calling it the sigma 2px, and then both of these orbitals here, there's 2 of them. These are what the problem is calling the pi 2p. Okay? Now each of these lines represents a single atomic orbital. Here in this notation, the pi 2p is representing 2 orbitals. Okay? So a single orbital can hold up to 2 electrons, but a doubly degenerate orbital like the pi 2p can hold up to 4. So you can put 2 paired electrons here, or you can put 2 paired electrons there in this other molecular orbital. Then you have their corresponding antibonding molecular orbitals. And then there's the antibonding molecular orbital associated with the sigma 2p. So what we want to do is fill these orbitals in with the electrons. Well, how many electrons do we have in this problem? Well, the K and the K, those take care of 4 of the electrons. What we're dealing with now are the valence electrons. So each oxygen contributes 6 electrons, so there's a total of 12 electrons that need to go into this molecule. So 2, 4, 6. Now we can add 4 to here. Okay, so we were at 6, we add 4 more, now we're at 10. We've got 2 more that can go in. Those would go here. So let's calculate the bond order. Here there's none. Okay, so that's not filled at all. So the bond order is going to be 1/2 the number of bonding electrons minus the number of antibonding electrons. So our stars denote the antibonding electrons. So the number of bonding electrons would be 2 plus 2, 4 plus another 4 gives us 8 bonding electrons, minus 2 plus 2 minus 4. That's going to give us a bond order of 2. So molecular orbital theory predicts that diatomic oxygen has a double bond. What about whether or not the molecule is diamagnetic or paramagnetic? Well, for that, it would be very helpful actually to have the diagram. So what I'm going to do is I'm just going to sketch out this electron configuration. So that would be the bonding orbital. Here's the antibonding orbital. Then we're going to have the pi 2p, and then we're going to have the pi 2p star, and up here will be that unfilled sigma star orbital. So we have 2 electrons here, 2 electrons there, 1, 2, 3, 4, and then we have 1 and 2. Okay. Notice that I'm satisfying Hund's rules here. I'm trying to keep the electrons maximally unpaired. So you still follow Hund's rules for molecular orbital diagrams. Notice that we've got 2 unpaired electrons. That means that oxygen, diatomic oxygen, in its ground state is paramagnetic. And that's exactly what's found experimentally. And so this is actually one of the great triumphs of molecular orbital theory, is that it successfully predicts that oxygen, diatomic oxygen, in its ground state is paramagnetic. That is, it has unpaired electrons. You might not expect that because it has an even number of electrons, but according to molecular orbital theory and experimental evidence, oxygen is paramagnetic. Well, I'm going to go ahead and leave the diatomic carbon to you as an exercise. So you need to figure out how to fill in these valence molecular orbitals, and feel free to use this diagram to help you determine whether or not diatomic carbon is diamagnetic or paramagnetic. You can also do the same thing for the diatomic carbon anion. You would just need to add an additional valence electron to the molecule, calculate the bond order, and use that to determine how stable the ion is. You can do the same thing for the diatomic doubly charged beryllium anion. And so I'm going to go ahead and stop this video here, and then we'll pick up in the next one with the next chapter, chapter 9, I believe.